connected to a larger disk of radius 20 centimeters and mass 1.5 kilograms. The block is released from rest. What is the block's speed after having fallen from rest for 1 meter? So let's start off by drawing our own sketch of this. So we have two disks attached to each other. The inner disk is radius r, the outer disk is radius 2r. Attached to the outer disk is a string. Imagine that string is wrapped around the inner disk, rather. Imagine it wrapped around the inner disk to an object of mass m. This object of mass m is then allowed to fall a distance of 1 meter. Question is, how fast is the block moving after falling for 1 meter? So here, it's another conservation of energy problem. In order to do this, we know we're going to need to know something about forces. So I know this mass has a gravitational force acting on it. It has tension acting on it. This disk has tension acting on it. It's a frictionless axle. No other forces I can identify acting on this. Now, if I use conservation of energy, it would be the change of translational kinetic energy plus the change of rotational kinetic energy plus the potential energies. So what's going to contribute to potential energy? Right. Yes, but what kind of force?
Gravity.
To potential energy? Gravity. Okay, what about tension? Is tension going to be a conservative force, or do we know if it's conservative or not?
Zero.
It is.
I think it's zero.
Is it zero?
Yeah.
I believe it's those two cancel out. Right?
It's other words.
Okay, so Lena?
It's opposite to motion, and it's we don't know if it's non-conservative or conservative, so we would put it with W other.
Yes. Since we don't know, we would have to find the work done by tension, depending on when I heard you say something. So what were you saying, Lynn?
I think if it goes like the opposite direction, those two can be cancelled out.
Okay.
Like we can declare sometimes.
So both of you are right. Lena is saying we need to consider tension as a work. Yes, absolutely. Nguyen is saying, well, if we create a system in which tension is an internal force, the work done by tension will sum to zero. So let's create a system that includes both the mass and these disks. If I create this system, so notice this mass is falling down, so the work done by tension on the mass is going to be positive or negative. The mass is moving down, tension on the mass is up. Is that positive work or negative work? Negative work. You guys don't know this yet, but, and I'll just write it. The work due to torques is given by this. That's the work due to a torque. Tension is a torque on this disk, causing this disk to speed up. So what's happening here is this disk is rotating clockwise, tension is clockwise. So you can think of the rotation and tension kind of being in the same direction. So here the work done by tension is positive. Here the work done by tension is negative. If they're part of the same system, these two works cancel out. So I'll just write it up here as a reminder that we hadn't forgot about it. Work done by tension on the mass and work done by tension on the disks. And these sum to zero because they are internal to the system. So what that means now is 1/2 translational kinetic energy. So now we have to figure out things. So I'll just say 1/2 mass of the block, speed of the block squared, minus its initial speed squared. So I'm going to use B to represent the block. So I'll add a subscript B to the blocks. So this is the kinetic energy of the block. And then plus kinetic energy of rotation. But we have two things rotating. We have the outer disk rotating. So let's call this rotational inertia of the 2r disk, omega of the 2r disk, minus omega naught of the 2r disk. I'm using 2r just to identify the outer disk. And this is the change of rotational kinetic energy for the outer disk, plus 1/2 I r omega r squared minus omega naught r squared. This is the change of rotational kinetic energy for the inner disk, plus mass of the block, final height of the block, minus initial height of the block, is equal to 0. Any questions on where I get this line? Okay. Well, let's figure out our initials and our finals. Our initial is here. It starts at rest. So nothing is moving. It has a certain height. I'll say its initial height is 1 meter. So I guess I'll create my coordinate system where the 0 is at the bottom. So our initial height is 1 meter. And we'll say the rotational inertia of the 2r disk is 1/2 mass of the 2r disk times 2 times the radius squared. Where do I get that from? Well, it's because I remember that the rotational inertia of a solid disk is given by that formula. So this is 1/2 the mass. I'll just call this mass 2r. I'll call this mass r. So mass 2r is 1.5 kilograms. Which is 3 times the mass of the block, isn't it? And then I'll just go ahead and call the mass of the inner disk. It is 1 kilogram, which is just 2 times the mass of the block, where the mass of the block is 1/2 kilogram. So here's all of our initial variables. Our final variables, we do not know the final speed of the block. We do not know the final angular speed of the inner disk, nor do we know the final angular speed of the outer disk. But because they are attached together, they will have the same angular speed. They're moving as a rigid body. So I'm saying the angular speed of the inner disk is equal to the angular speed of the outer disk. Final height of the block is equal to 0. So let's go ahead and cancel some things out. Initial speed is 0, initial angular speed is 0, initial angular speed is 0, final height is 0. So then we have 1/2 mass of the block, speed of the block squared, plus 1/2 I. This is rotational inertia of the 2r disk, omega squared, plus 1/2 times 1/2 oh, I forgot my R. Right, I need more space. So rotational inertia of the outer disk is 1/2 mass of the disk times its radius squared times its angular speed. So that's this expression right here. Plus 1/2 rotational inertia of the inner disk, which is 1/2 mass of the inner disk, radius of the inner disk, times its angular speed squared, minus mass of the block. Oh, and I forgot my G here. G, initial height of the block, is equal to 0. So I'm going to just say let M be equal M, because I could say 1/2 M VB squared plus, well, let's look at this. This is 1/4 times 4, well, mass 2R. Mass 2R is 3MB. So here I'm going to replace with 3M. This is 4R squared, omega squared, plus 1/4 times 2M times R squared omega squared, minus mg y naught b is equal to 0. Notice mass, 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 mass. That's why it took time to figure out the relationships, because it was simple enough. So all the masses go away. Our goal is to find final speed. I see I have 4 as a denominator, so I'll just multiply through everything by 4. Well, that cancels with that. That's nice. So when I multiply through everything by 4, that's a 2VB squared. 4 times 3 is 12R omega squared. And then we have 4 times this is 4, so that is 2R omega squared minus 4GY naught B is equal to 0. Actually, I should have multiplied by less because we have it by 6 instead of 4, but oh well. That's okay. So now we can combine these two, right? You know, and we can factor out by 2 if we want, but I'll just keep it like this so I don't do too many things at once. So this is just 14R omega squared equals 4GY naught B. What do you think R omega is equal to?
Velocity.
Speed of what? Why, though? Because R and omega corresponds to this disk, not to the block.
Because it changes. Because you consider it as one system, so the block will one speed, the disk will move at the same speed.
But what about this point on the disk? Will this point on the disk have the same speed as this point?
No, but it's not attached. The string's not attached.
This is attached here.
We'll have the same angular velocity.
Same angular velocity, but not the same
The
speed.
velocity over the radius. So it's because the radius is higher, it will make up for.
No, now you're getting further from the truth.
Really?
Yeah. Shot it.
Is that because the loop is rotating according to the R and the speed is?
Yes. I guess I'm looking for certain things in your answer. It's not. It's probably more straightforward than you realize. here's a point on the string. What can you say about the speed of this point on the string with the speed of this point on the string?
They're the same.
They're the same. What can you say about the speed of this point on the string and the speed of this point on the outer hoop?
2,000. Not less.
They're not the same. Why aren't they the same? V equals R omega. So even though they might have the same omega, they have different radii. So we can't say that V corresponds to the outer disk because V depends on radius. But what we can say is every point on the string moves with the same speed, including this attachment point right there, which means every point on the circumference of this disk is moving with the same speed. So I just didn't want you to automatically associate R omega with the speed of the block without thinking why. Why R omega is the speed of the block is because specifically, and why we can connect it to this disk is because the speed of every point on the perimeter of this disk is the same as the speed of every point on the string. So I just wanted you to go through that exercise because it's very common to get a problem saying, oh, R omega, this speed must be the same as that speed, and in some of those situations, you'll get it wrong. So at least think about what objects does this speed correspond to. Akshay, did you have a question? Love your haircut, by the way. I thought you had a question, but not?
No, I'm good.
Okay. So any questions so far? Okay, so now we can say the speed of the block is the same as the speed of the perimeter of the inner disk. So I will say this. I'm really wishing that I had only multiplied by 6, but that's okay. It's just algebra. We'll just do some more steps. So this is just 16 VB squared is equal to 4GYB. So VB is equal to 1/4 GYB. I just divide it through by 16, and it's the square root of that. You guys know my question. What's the answer? Yes, we've seen this before. Square root of G and a height underneath.
That's why we solve
Free
in terms
fall?
of variables.
What was that?
That's why we solve in terms of variables.
Yep, you've heard it before.
If you use numbers, you wouldn't see the pattern.
Exactly. Thank you. Next semester, I want you to come back and teach for me.
Yeah.
Because you know what I'm going to say already. Okay.
So is it like the free fall?
Is it?
I think, oh yeah.
Free fall is this. So it's similar, and it's what Larry just
Oh.
said. So I'm not going to repeat it because he said it better than I said it. Okay. Any questions on this? Okay, so now that we know about rotational kinetic energy and how to handle these problems, after the break, we're going to return to torque, and we're going to go back and start doing some torque.